trigonometry to another section in right triangles. This time we're going to be looking at a very special topic in right triangles called trigonometry, which trigonometry just means the study of triangles. And so we're going to look at a lot about how the sides relate to each other and how the sides relate to the acute angles in a right triangle. We found out in the last section and the previous section that when we have similar triangles, the proportions are equal. And with right triangles, if you know one of the acute angles, this is going to be similar to every other right triangle that has that same acute angle because of the AA similarity theorem. So what's also true about similar triangles, not only are these going to be proportional to the corresponding sides on another triangle with those same angles, but the ratios of the same sides in reference to that angle will always have the same ratios. I'll show you what I mean. So the first ratio we're going to talk about is called the sine ratio. And everything is going to reference one of the acute angles. We're going to call that angle, it's frequently called in trigonometry the Greek letter theta. So this looks like kind of an O with a slash through the middle of it. This is the Greek letter theta. Theta, T-H-E-T-A, theta. It makes the TH sound in the Greek alphabet. So the Greek letter theta, this is going to stand for the angle. So this is the sine of that angle is actually going to refer to the opposite leg divided by the hypotenuse. And one way that we're going to remember that relationship, that the sine ratio in this right triangle, the sine ratio of that angle, is the opposite leg compared to the hypotenuse, is this abbreviation SOH. Sine is the opposite leg over the hypotenuse. SOH, sine opposite hypotenuse. So in this triangle here, if I wanted to say what's the sine ratio for x, we're referring to this angle here, this x. The sine ratio is the opposite leg. Opposite is just the leg across from the angle. So the opposite leg compared to the hypotenuse, opposite to hypotenuse, so 5 over 13. And so why this is useful is this, if the sine of x is 5 over 13, that allows us to describe the ratio of the opposite side to the hypotenuse in any triangle that has that same angle measurement. So if this was 5 over, or if this was 10 over 26, for instance, 10 over 26 reduces to 5 over 13, it would have that same angle measurement there. Here, if I'm talking about the sine of y, sine still refers to the opposite leg over the hypotenuse. Hypotenuse, remember, is the leg or the side of the hypotenuse, side of the triangle across from the right angle. So opposite over hypotenuse is going to be 6 over 10, and that reduces to 3 over 5. So the sine of y is 3/5. The ratio of the opposite leg to the hypotenuse is 3/5. So any triangle that has that same angle measurement will have that same sine ratio, just scaled up or scaled down. So let's use the sine to solve for x. So since we specific sine ratios will always have the same, or specific angles will always have the same sine ratio, we can use that sine ratio for that specific angle to solve for a missing side. So we're going to be able to say the sine of 40, so just like we had sine of x is 5 over 13, sine of y is 6 over 10, sine of 40 equals the opposite and hypotenuse here. Oops, hypotenuse. Let me rewrite that. So opposite hypotenuse, 7 over x. Sine of 40 equals 7 over x. Once we've written that ratio, we can then use our calculator. So on your calculator, you've probably noticed the SIN, the COS, and the TAN buttons. So the sine, cosine, and tangent are what those are. And we'll talk about cosine and tangent again in a little bit. This first one, though, for a sine, the sine ratio, if we type in, and for my calculator, I type in sine and then 40. Okay. If you're using your phone calculator, some phones you have to type in the 40 first and then type sine, and it will evaluate the sine of 40 that way. So it kind of depends on your calculator. This is how we would enter it in on the calculators you'll have access to on the learning checks and on standardized tests. So sine of 40, we'll close that parenthesis if there's our parenthesis. Okay, so when we evaluate that, we get this 0.6427876097, this big messy decimal, kind of like we get when we take square roots. We get this irrational number. So with the sine of 40, what we're going to do with that, we could write down the decimal if you want, but any decimal that we write down is going to be rounded. So what I'm going to do instead is just keep that as sine of 40 until I have to use it. So when I'm writing down my equation, sine of 40 equals 7 over x. And remember, these are ratios. This is a ratio. Sine of 40 is this ratio, 7 over x. So what we can do is we can treat this side of the equation also like a ratio. Anything over 1 is itself. So sine of 40 over 1 equals 7 over x. And then we can use the cross products, just like we do in any other similar figure. X times the sine of 40 is equal to 7 times 1. And then we can divide by the sine of 40. Divide by the sine of 40. So that cancels that out there. So take x divided by the sine of 40. So in my calculator here, I can do some rewriting here. 7, this is 7, divided by the sine of 40. And so while the sine of 40 itself was like 0.6 something, when I divide 7 by the sine of 40, I'm dividing by that scale factor that relates the opposite side and hypotenuse. And I get this 10.89. Okay, so in this case, x is 10.89. We want to check our answer. We can make sure that our sine ratio equals what it's supposed to. So it should be 7 over 10.89. So when I divide 7 by 10.89, I get 6.4, or 0.64279, etc. Now it's off by a little bit because I had to round, but you see that's that 0.64. And when we typed in the sine of 40, we also got the 0.64. Okay, so the ratio of the opposite to hypotenuse is equal to the correct sine of 40. And I think it's a little bit blurry. There we go. It might be a little bit better. Okay, so let's look at one more here. So here I have this 50 degree angle, and so if I want to find out what x is the opposite leg, and the hypotenuse is the side across from the right angle. So the trig ratio that compares opposite to hypotenuse is the sine ratio. So we're going to say the sine of the angle, sine of 50, equals x over 18. X over 18. And we can think of this in the same way, put that over 1. In this case, when we do the cross products, x times 1 is just x, and you can just multiply by 18. So 18 times the sine of 50, 18 times the sine of 50. So if I type in my calculator 18 times the sine of 50, I get 13.78. So I'll round that to the nearest hundredth. So 13.79. So x in this case is 13.79. Now if I want to see is that going to get me the correct sine ratio? Does this answer make sense? If I divide 13.79 by the hypotenuse, so opposite divided by hypotenuse, 13.79 divided by 18, I get this 0.766, and if I type in the sine of 50, I also get that 0.766. Okay. Now the decimals are always going to be off by a little bit because I'm rounding when I write that decimal out. Okay. So, but just look at the first couple decimals and it should be accurate enough. Okay. So this, oops. So there's our other side here, the opposite over hypotenuse, the ratio. So that sine ratio, the sine ratio of that 50 is going to be the sine ratio on any right triangle that has a 50-degree angle. And just like when we find the sine of 40, the sine ratio on any other right triangle that has that same 40-degree angle, the sine ratio will be the same. And so remember, with similar figures, that doesn't mean that the sides will be the same. It means the ratio of the sides will be the same when we divide. So we're going to do this last one. We're going to do this last one together in class. For now, I'm going to skip on to the next trig ratio, which is the cosine. The cosine. So cosine. So just like with the sine ratio here, we abbreviate it SIN, but it is the SINE is how the word is spelled, sine. So we use SIN. The cosine is just COS, cos. Okay. Now what the cosine is it's the sine of the other angle. It's the sine of the other, the complement to this one. So if the sine of this other angle, the opposite over hypotenuse, that side that's opposite that other angle is adjacent, it's next to the angle we're referring to. So if this is theta here in the corner, this is the adjacent leg. Adjacent just means next to, right? And the hypotenuse is still the hypotenuse, the side across from the right angle. So this is the adjacent leg over the hypotenuse. Hypotenuse. Okay, adjacent leg over hypotenuse. So once again, cosine, it's called that because it's the sine of the complementary angle. It's the sine of the other acute angle. So in this one, when I want to refer to the cosine of x, that's the adjacent leg over the hypotenuse. And we can remember that using a three-letter abbreviation, CAH. The cosine is the adjacent over hypotenuse. Adjacent over hypotenuse. So this is, the adjacent leg is 12, and the hypotenuse is 13. 12 over 13 doesn't reduce, so that's it. We're done. The cosine of x is 12 over 13. The cosine of y, in this one, the adjacent leg is the 36, and the hypotenuse is the 39. So 36 over 39 is going to be the cosine of y, adjacent over hypotenuse. Okay. Adjacent over hypotenuse. And we can reduce that. 36 over 39 reduces to, let's see, 3 goes into both of those. 3 goes into that 12 times, and 3 goes into that 13 times. So these actually have the same cosine ratio, which would mean that y and x would actually have to be the same angle measure. X and y would have to be the same angle measure if they have the same ratios. Okay. We know that the figures are similar. This one's just twice, or this one's 3 times as big as that one, right? 5 times 3 is 15, 12 times 3 is 36, 13 times 3 is 39. So they have the same ratios, which means they have the same angle measures. Kind of cool. So just like with the sine, we can use cosine ratio of a specific angle to help us find missing side lengths. So this 5-degree angle here, or 15, that's a 15. Okay, that's a 15-degree angle. 15 degrees. So we're going to look at the sides that we have. This 22 is the adjacent leg, and this is the hypotenuse. So for the adjacent and hypotenuse, we're going to use the cosine. Cosine of 15 is equal to the adjacent leg, 22, over the hypotenuse, x. This is a ratio. We're going to treat it like a ratio. Put the cosine of 15 over 1, and then we can multiply the cross products. So x times the cosine of 15 equals 22 times 1, or just 22. And then remember, evaluating the cosine of 15 is going to get me a messy decimal, probably. So let's try it out. So the cosine of 15 gets me this 0.96592, etc., right? So I probably don't want to have to write that out or write a rounded version. I'm going to get a less accurate answer if I have to round the decimal. So we're going to instead of evaluating the cosine of 15, we're going to keep it as the cosine of 15. That's just a number. And we're going to divide both sides. We're solving for x, so we're going to divide by the cosine of 15, divide by the cosine of 15, just like we would in any other proportion that we're solving. We divide by the coefficient on x. So 22 divided by the cosine of 15 gets us 22.776. 22.776. I'm going to round that to the nearest hundredth, 22.78. Okay, so x is 22.78. Now, to check my answer, remember adjacent over hypotenuse. So if I take 22 divided by 22.78, okay, 22 divided by 22.78, I get that 0.96, more or less, like 0.97. And if I type in the cosine of 15, I also get that 0.97. Okay, so I've found the correct hypotenuse here. Okay, the ratio of those sides is the cosine of 15. The ratio of adjacent to hypotenuse in any other triangle, in any right triangle that has that 15-degree angle. Let's do one more. We have this 61-degree angle here. The x that we're trying to find is the adjacent leg. Oops. Adjacent, and the 18 is the hypotenuse. So the trig ratio that uses adjacent or that compares the adjacent and hypotenuse is the cosine. So we're going to say the cosine of 61 is equal to x over 18, where it's always adjacent over hypotenuse. So in this one, we didn't know the hypotenuse, so the x was on the bottom. This one, we don't know the adjacent leg, so the x is on the top. And then we can either put this over 1, or we can notice that 1 times x is just going to be x. So I can just multiply by 18 on both sides to get x by itself. And so x is going to be equal to 18 times the cosine of 61. So let's type that in. 18 times the cosine of 61. Close our parentheses and hit enter. We get 8.73 about. So 8.73. And if we check our answer, we can take 8.73 divided by 18. Divided by 18. We're looking at the ratio of the adjacent leg to the hypotenuse. We get 0.4848, etc. Okay, and if I evaluate the cosine of 61, I get that 0.4848. Right? So we just want to look at those first couple decimals, make sure that those are the same, and we have ourselves our missing side. So this is a really powerful tool for finding missing sides when you know the angles in these right triangles. We're going to skip over this next one. We'll do that together in class. And we're going to look at our final trig ratio, the tangent ratio. So the tangent ratio, so this is tan is for tangent. The tangent ratio compares the opposite leg to the adjacent leg. Okay, opposite leg to the adjacent So now we have a way of comparing every single pair of sides. We have opposite to hypotenuse, we have adjacent to hypotenuse, and we have the opposite to the adjacent. So in this one, x is our angle, the opposite leg is the 2.5, the adjacent leg is the 0.6, and we can reduce the fraction. Now, in this case, they're both decimals, so our reduced fraction, we could try dividing in our calculator to see if we have an obvious answer for us. So if I go 2.6, oops, that's 2.5 divided by 0.6, I get this 4.16 repeating. And I don't know that off the top of my head necessarily what that's going to be as a fraction. What I can do instead is I can, since I know decimals, I can multiply both by 10 to move the decimal one place to the right. So that'd be 25 over 6. And 25 and 6 don't actually have any common factors, so that is our reduced fraction, 25 over 6. So you can, even with decimals, you can write a reduced fraction with integers if the decimals terminate. And so in this one, I have the tangent of x. X is this one. So the side opposite x is 7. 7 over 24. The 24 will be the adjacent leg. And with y, 24 is the opposite leg. So 24 over the adjacent leg is 7. So the tangent of one angle will be the reciprocal of the tangent of the other one. 7 over 24, 24 over 7. Just like with the sine and cosine, we can use the tangent ratio to solve for the missing side. So we can say we're looking for this opposite leg here. We know the adjacent leg, and it's the tangent ratio that uses opposite and adjacent. So we'll say tangent of 12 equals x over 15. And then we can multiply by 15 to find that x is 15 times the tangent of 12. So we'll type in 15 times the tangent of 12. And we have oops, that's not what I wanted. There we go. 3.19. So 3.19. And remember, we should expect the side that's across from the smallest angle to be the smallest side. So the 15 is much bigger, that angle is bigger, 12 is the smallest angle it looks like, so x, that's going to be our smallest side. And of course we can check our answer by dividing 13.19 by 15 and check that it's the same as the tangent of 12. Let's do this last one here, and then we'll do the number 15 in class together. So the tangent, and it's tangent because we're looking for this opposite leg here, and we know the adjacent leg. Looking for the opposite one, we know the adjacent one. So we have the tangent of 58.1 equals opposite x over adjacent 28. And notice in both of these ones, we had the x on the top, and that's usually the easiest way to solve is when we have the x on top. So this kind of worked out nicely for us. So we're going to multiply both sides by 28. Multiply by 28. So x is 28 times the tangent of 58.1. 28 times the tangent of 58.1. We get 44.98. 44.98. The 58.1 will be the larger of the two angles, even though the drawing isn't to scale. 58.1 should be the bigger of the two acute angles, because the two acute angles should add up to 90, right? Remember that from our section on interior angles and right triangles. So we could subtract that from 90 to find that this should be like 30 point something, 32.9 or 31.9. So this actually should be the smaller of the two sides. So even though the drawing doesn't show it, that actually is correct. Okay, we'll stop there. We'll look through those last couple ones in class together, and we will spend several days on this. I know this isn't the end of RTT6. This is just part 1. We'll look at part 2, looking at the inverse of trig functions, actually finding out what that angle is. We'll look at that in the next one. So bye for now.